Hi everyone, this is Dr. Nak, and today what we're going to do is we're going to be solving exponential and logarithmic equations. Here is our first property. It's called the one-to-one property of log equations. So basically it says that if log base a of m equals to log base a of n, then m must be equal to n. Alright, so let's do some examples. Example 1, solve 2 log base 3 of x equals log base 3 of 36. Before we do anything, let's bring our 2 and then rewrite it as an exponent on the argument of x. So if I do that, then what we're going to get is log base 3 of x squared equals log base 3 of 36. Now notice that we have the same base. So that means that what we can do is we can equate the argument of the log base 3's together. Alright, so this implies that x squared must equal to 36. Now all we have to do is solve from here. So applying the square root property, let me see, if I take the square root on both sides, remember you're going to have a plus and minus, right? So this implies that our x is plus or minus the square root of 36, which is plus or minus 6. Now make sure to check your solution because, I don't know if you remember this, the argument of the log has to be greater than 0, meaning log base anything of 0 is undefined and log base anything of negative numbers are undefined. So in this case, if I plugged it in, x equals negative 6 in here, well, we're safe because negative 6 whole quantity squared will give us a positive number. So we get to keep both plus positive 6 and negative 6 as our solution. All right, so I'm going to write it as, therefore, our solution set is 6 and then negative 6. And that's going to be the answer. Let's do another one. Example 2. Log base 3 of x plus log base 3 of x minus 8 equals 2. Alright, so first step is this. What I would do is I would like to combine this maybe in one log. So, do you guys remember this one? Log base b of m plus the log base b of n. This was log base b of m times n. So if I use that property, I can condense these two logs into log base 3 of x times x minus 8. And then this whole thing is going to equal to 2. All right, now what do we do? All right, let's recall this property. So if we have b to the log base b of m, this is going to equal to m. So you can think of it as if the big base b and log base b, if b's are the same, then they're going to cancel each other out. But anyways, so let's raise both sides on top of 3. So what I'm going to do is I'm going to raise 3 to the log base 3 of x and then x minus 8. Now if you're going to raise the left hand side over 3, then you better do the same thing on the right hand side. So I'm going to have 3 squared. Now using this property over here, what we're going to get is x and then x minus 8 equals 9. All right, looking good. So now I'm going to distribute the x in. Then what we're going to get is x squared minus 8x equals to 9. All right, remember what we're doing. We're trying to solve for x. So I would like to bring the 9 on the left-hand side by subtracting 9. So we get x squared minus 8x minus 9 equals 0. Now we factor. So let's see what we get. I'm going to set the right hand side to be 0. So I better have an x and an x here. And maybe minus 9 and then plus 1. Would that work? Yep, so it should work. All right, so that implies that, now let me just go over here. Either x is 9 or x is negative 1. Now, I didn't box this yet because I need to check my solutions. Make sure to check your solutions. All right, so what you do not want to have is that argument of the log has to be strictly greater than 0. So if the argument of the log becomes a negative number, we need to toss that proposed solutions away. All right, so keep that in mind, and I'm going to check my solution. So which is first x equals to 9. Okay, I'm going to plug that in the very top equation that we got. So we got log base 3 of 9 plus log base 3, that's a 3, of 9 minus 8. Is that going to equal to 2? All right, so this is what we need to check. Now, log base 3 of 9 can be written as log base 3 to the 3 squared, and then plus log base 3 of 1. So now, log base 3 of 3 to the second power, you just get the exponent back, and then plus log base anything of 1 is always going to be 0. So this is going to equal to 2, which matches up. All right, so therefore, we're going to keep solution set as 9 for sure. All right, now let's check for x equals to negative 1. I'm running out of room here, so let me just go like that. All right, so let's check x equals to negative 1. All right, let's see what's going to happen. So if I plugged in a negative 1 into here, notice that the argument of the log becomes negative, and over here as well, right? So in this case, you're going to have to toss that solution away. So I'm just going to say bye-bye. All right, so it looks like our solution set is just 9. Oops. All right, so I'm going to box that for our answer. Okay, let's do another one. Example 3, solve log base 4 of x plus 6 minus log base 4 of 2x plus 5 equals negative log base 4 of x. Now it looks really, really ugly, but we got this. All right, so first step, what I would do is I would like to combine the left-hand side together. Okay, so again, we can use this property. So let me just write it. Log base b of m minus log base b of n. This is log base b of m over n. All right, so I'm going to apply this on the left-hand side. And then on the right-hand side of the equation, notice that if I have something like maybe log base b of m to the p, this is same thing as p times the log base b of m. All right, so keep that in mind. Now let's work it. So first, let me combine these two by using the first property that I wrote down. So this is same thing as log base 4 of x plus 6 all over 2x plus 5. And then on the right hand side, I'm going to use the second property here. So what's going to happen is that this negative 1 is going to be in an exponent on x. Okay, so here I could rewrite this as log base 4 of x to the negative 1. Let me just put a parentheses so that you can see which is the argument and which is the base. All right, now we have this situation, right? We got log base b of m equals to log base b of n. This implies that m must equal to n, right? So what we can do now is we can equate the argument of the logs together. So next step, x plus 6 over 2x plus 5. This is going to equal to x to the negative 1. All right, but the last time I checked, x to the negative 1 is nothing but 1 over x. Let me rewrite it nicely. So we got x plus 6 over 2x plus 5 equals 1 over x. Now we got to solve that sucker. All right, so if I were you, how about the cross multiplication? All right, or you can multiply by the least common denominator, which will be x times 2x plus 5 on both sides. It's going to be the same thing. So if I cross multiply, I'm going to have x times x plus 6 equals 1 times 2x plus 5. So that's just 2x plus 5. All right, looking good. Now I'm going to distribute the x. We get x squared plus 6x equals 2x plus 5. All right, now I'm going to subtract 2x. And might as well just bring the 5 over as well. I'll just do everything step by step. So we got x squared and then plus 4x all right, equals 5. All right, now I'm going to subtract 5. That is a 5. All right, and then what we're going to get is x squared plus 4x minus 5 equals 0. From here, we factor. All right, so what do we got? We better have an x and an x. Sign better be, what is that? One has to be positive, one has to be negative. So how about 5 and a 1? I think that should work. All right, so that implies that either x is negative 5 or x is positive 1. All right, those are our proposed solutions. Okay, so now we check. All right, so let's check x equals to negative 5. And let's plug him in. All right, so if I plugged it in, negative 5, in place of x over here. So here, do you see that? I can rewrite this as log base 4 of x to the negative 1 is 1 over x, isn't it? So if I plugged it in, x equals to negative 5 here, do you see that our argument of the log becomes negative 1 over 5, which is an illegal maneuver. All right, so we have to toss this guy away. Bye-bye. All right, now let's check when x is 1. I'm going to plug this 1 into the top equation. So let me just write it over here. So we have log base 4 of 1 plus 6 minus log base 4 of 2 times 1 plus 5. Is that going to equal to negative log base 4 of x is 1? So log base 4 of 1. So let's check. All right, so the left hand side, what do we got? We have log base 4 of 7 and then minus log base 4 of 7. Oh, look at that. All right, and then this becomes just a 0. All right, now let's check this side. On the right hand side, I don't know if you see this or not. Log base anything of 1. Do you guys remember? This is always going to equal to 0. All right, so 0 equals to 0. So x equals to 1 is a solution to our log equation. So let me just write, therefore, the solution set is just 1. All right, here's our answer. All right, so from example 1 through 3, we're solving log equations. So now let's take a look at solving exponential equation. All right, so let's take a look at example 4. Solve a to the x equals 98. Find the exact answer and then approximate it to 3 decimal places. So please get your trusty calculator out because we're going to have to use your calculator for the second part. All right, but let's first go with the exact answer. So do you guys remember this property? So I'm going to use this. If I have a log base b of b to the x, this just becomes x. So you can think of it as if the little b and big B matches up, then what you're left with is just the exponent on the base b. All right, but anyways, I'm going to apply this property because remember what we're doing. We're trying to solve for x, but right now this x appears as an exponent. So I need to bring that guy down. All right, so how do I do that is to apply the property that we just wrote. So I'm going to attack both sides by log base 8 of 8 to the x equals. Now if I'm going to take log base 8 on the left hand side, I better be fair and do the same thing on the right hand side. All right, so this is what we got. So now what do we got? Little base 8 and then big base 8, yes, they match up. So what we're going to get is just x equals log base 8 of 98. So this will be the exact answer. So I'm going to box this as an exact answer. Or maybe I should put that in the solution set, but oh well. All right, so now what we need to do is we need to approximate log base 8 of 98 to 3 decimal places. So if you look at your calculator, right, do you see log base 8? I don't think so, because only button that you have is log base 10. So it should just say log. Or ln, which is the natural log. Okay, so what we're going to do now is, guess what? Just so that we can type this in the calculator, we're going to have to apply the change of basis formula. All right, so let me just write that out. Change of basis. All right, so it says that if I have a log base b of, let's just call it m as an argument, you can change that base b into anything, which is just, you can just go log base 10 of m over log base 10 of b. Or you can even go, if you like natural log better, you can just write ln of m over ln of b. So these are the arguments of the logs. Whichever you like. I usually like the natural log better, but it's up to you. Your answer will be exactly the same. Alright, so from here, what I'm going to do is apply the change of base formula. So let's go with, I'll just go with log base 10. So I could rewrite this as log of 98 over log of 8. All right, now bust out your trusty calculator. Now, if I type in log of 98, I get, this is going to be approximately 1.99122. Don't worry, I'm going to approximate this at the 3 decimal places at the end. I'll just keep it right there. And then whole thing over, now let's go with log of 8. So if I type that in there, I got 0.903, 089987, but I'm just going to stop right here. So now let's divide 1.991226 divided by 0.9030899. All right, so you're probably going to be able to do this much faster than I am. So 1.991226 divided by 0.9030899. All right, so I got this value to be approximately 2.2049034. Now I want to approximate it to 3 decimal places, so I need to chop it off right here. So it looks like our approximation is going to be 2.205. All right, so I'm going to box that for the answer. Now, if you have a scientific calculator, you did not have to compute log of 98 first, and then exit, and then log of 8 next. You can just simply type in log of 98, whole thing divided by log of 8. But here what I did was I just computed log of 98 and log of 8 separately, and that's all. All right, so that is that. Now let's look at the next example. Solve 2 times e to the x minus 2 equals to 18. So first we're going to get the exact answer, and then we're going to use our trusty calculator to approximate the value. All right, so let's first isolate that e first. So how do I do that is by dividing by 2. So let me just write the whole problem out. We have 2e to the x minus 2 equals to 18. And I'm going to isolate the e, so I need to divide both sides by 2. So then what we're going to get is e to the x minus 2 equals 9. Alright, now since we're trying to solve for x, I need to bring that x downstairs. He cannot be as an exponent, so we need to apply this property right here. Who kills e is the natural log. So ln of e to the x, you guys remember this one? This is going to become just x itself. Alright, so what I'm going to do is I'm going to attack both sides by ln. So this is what I'm talking about. If I compose both sides with ln, I'm going to have ln of e to the x minus 2 equals ln of 9. Alright, now this portion, by the property that we learned earlier, this just becomes now x minus 2 equals to ln of 9. Now remember that ln of 9 is just a number, some decimal value. Okay, so this is just a number, so don't freak out. All right, so now let's solve for x. How do I solve for x? Is just adding 2 on both sides. All right, then we get x equals ln of 9 plus 2. So the solution set is ln of 9 and then plus 2. So this will be the exact answer. All right, so I'm going to box this. And now we are going to approximate by using our calculator. Okay, so first find that natural log button. So you should just say ln. I'm going to write ln of 9 in parentheses and then plus 2. And then hit enter. And what I got was 4.197224577 or something like that. But I need to approximate this at 3 decimal places. So I need to chop it off right here. So what do we got? So approximate value is 4.19 and then 7. So there is that. Okay, so our next topic is compound interest. So let's just read this together. It says that for principal P invested at an interest rate R for T years, then the new balance A is A equals P times the quantity, 1 plus R over N, raise it to the N times T when compounded N times a year, and A equals P times e to the RT when compounded continuously. So let's just summarize this. We got so many notations going on. So A is the new balance, P is the principal, R is the interest rate, T is time in years, N is the number of compound per year. All right, let's take a look at example 5. Maria's parents put $10,000 in investments for her college expenses on her first birthday. They hope the investments will be worth $50,000 when she turns 18. If the interest compounds continuously, approximately what rate of growth will they need to achieve their goal? All right, so let's first underline what's important. What information are we given? So first of all, Maria's parents put down $10,000 in investments. So this is the amount that they put down first. So this is nothing but our principal. All right, and then let's just read it through. Her college expenses on her first birthday. All right, and then they hope the investments will be worth $50,000 when she turns 18. So the $50,000 is our outcome that they want. So this is going to play the role of A, which is the new balance. Now, if the interest compounds continuously, now that's another important stuff because remember there were 2 formulas for the compound interest. So we need to pick the one with the compounded continuously, which will be A equals P e to the RT. So let me just underline that as well. All right, approximately what rate of growth would they need to achieve their goal? So what are we looking for? What rate of growth, right? So what we're looking for is rate of growth, which is R. So let me first write down what we're given. Okay, so our A is $50,000. That will be the new balance that they're looking for. And then our P, principal, is how much money do they put down? Well, they put down $10,000. Gosh, Maria is so lucky, huh? All right, now R is what we're looking for. So I'm going to put a little question mark there. And T will be the time in years when Maria is going to get her $50,000. So let's carefully read this problem. So notice that her parents are going to give her $10,000 on her first birthday. And then she's going to get that when she turns 18. So what's the value of t? Is it 18 or is it 17? It's 17 years. All right, so I'm just gonna write down as 17 years. And I think we are good to go. So let's first write down the compound interest formula that we're gonna be using for this is A equals P e to the RT. Now remember, R is what we're looking for. All right, so let's plug in all the values that we have. So we have 50,000 equals 10,000. I'm just going to put a parentheses here, times e to the R, and then t is 17. All right, now let's just simplify this equation a little bit. Let's divide both sides by $10,000. So just simplify. You don't have to do this portion if you don't want to. You can just type that 50,000 and 10,000 in the calculator, but I like to deal with smaller numbers. So if I did that, then what we're going to get is 5 equals just e to the 17r. All right, looking good. All right, so now remember we're trying to solve for r, but our r is right now is on the exponent on e. So I need to kill that e. So who's going to kill it is ln. So what we're going to do is we're going to compose both sides by the natural log. So we're going to have ln of 5 equals ln of e to the 17r. All right, now remember again, ln of 5 is some kind of numerical value, decimal value that you're going to get. And now on the right hand side, applying the log property, we're just going to have 17r. Yay, so we're almost done. So that implies that our r is ln of 5, whole thing divided by 17. All right, now we need to approximate this. So I'm going to type this in the calculator. So I'm going to do this with you. So you can do it with me too if you like. So you got ln of 5 divided by 17. So this value, I got 0.094678, yada yada yada. All right, so let me just where should I round off at? Maybe to the 3 decimal places. So I'm just going to round it off at 3 decimal places then. So then our r is 0.094. 5. All right, at the very last step, we need to convert this in terms of a percent. So what do we need to do is we need to take this decimal place and move it to 2 places to the right. So it looks like our r is going to be 9.5%. So our answer is going to be, let me just write down everything in sentence. So the parents need the rate of growth to be approximately 9.5%. All right, so I'm just going to write it as Maria's parents need the rate of growth to be approximately 9.5%. Whatever the percentage is, Maria is one lucky girl. That's all I have to say. All right, so here it is. Okay, so our next topic is exponential growth and decay. Okay, so it says that for an original amount, a sub 0, that grows or decays at a rate k for a certain time t, the final amount, which is denoted by a, is given by a equals a sub 0 times e to the kt. All right, so here's the summary. A denotes the final amount, a sub 0 is the original amount, k is the rate of growth or decay, and t is time. Now k, when it's growing, your value of k has to be positive. So if it's growing, then k is positive. And it's decaying, then our k should be negative. All right, so let's do an example involving the exponential growth and decay. Let's take a look at example 6. A certain bacteria population grew from 200 to 500 in 4 hours. At this rate of growth, how many bacteria will be there in 24 hours from the start? All right, let's do the same thing as the previous example. Let's just underline what's important. So first, bacteria population grew from 200 to 500. All right, and how many hours? That will be 4 hours. Now let's just jot down what the question's asking. At this rate of growth, how many bacteria will there be in 24 hours from the start? At this rate, right? So it looks like we're looking for a rate of growth. Rate of growth. So I'm just going to underline that. Keep that in mind. And let's just list out what stands for A sub 0, K, and a T. All right, so first, we're going to be using this formula, A equals A sub 0 and then e to the kt. Let's recall that A is the final amount, A sub 0 is the original amount, K is the, in this particular problem, rate of growth, so K better be positive, and T stands for time. All right, so let's first go with A. So A is the final amount of the bacteria population, so if I read it very carefully, population grew from 200 to 500. So that means that final amount should be 500 and then original amount should be 200. So let me write that out. So let me just go with our A is 500 and then our A sub 0 is 200. And K is the rate of growth, but that's what we're looking for. So I'm just gonna write equals question mark. And T is the time from the starting number of bacteria to the end number of bacteria. So how long did it take to grow? 4 hours. So in this case, our time is going to be 4 hours. I'll just put it as 4. I'll just put hours, why not? All right, so I think we are good to go. So let's plug all the values in. Let me rewrite the formula for this. So we have A equals A sub 0 e to the kt. All right, so A is the final amount, which is 500. A sub 0 is the original amount, which is 200. And then here you're going to have e to the kt. Well, k is what we're looking for, and t is 4. So here you're going to have 4 times the k. Now I'm going to divide both sides by 200. Then what we're going to get is 5 over 2 equals e to the 4k. All right, now in order for us to solve for k, I need to get rid of the e. So what do? Yes, compose both sides by ln. Natural log of 5 over 2 equals natural log of e to the 4k. All right, now ln of 5 over 2 is again some kind of a decimal value. And here you're going to have 4k. All right, now almost home. Dividing by 4. So what do we get? Our k is ln of 5 over 2, whole thing divided by 4. All right, now bust out your trusty calculator. Type in ln of 5 over 2 and then whole thing divided by 4. And I got this value to be 0.22907 something something something. So let's just round this off at a 3 decimal point. So let me see, it's right here. All right, so then it looks like our k is approximately 0.229. All right, let me box this. Okay, so we found the rate of growth. That's great. All right, so we're here. Okay, so we got rate of growth. Okay, now how many bacteria will be there in 24 hours with the rate of 0.229? So the next step, what we need to do is we need to use this rate of growth to predict the number of bacteria there is going to be in 24 hours. So guess what? We're going to have to reapply the formula again. So in this case, what we're looking for is the final amount of bacteria, which will be A. So let me just rewrite. So next step, our A is the final number of bacteria at the end. And notice that this is what we're looking for. A is what we're looking for. So let me just write down question mark. Now, our A sub 0 was the original amount of bacteria, so that's 200. And then now we have a K. K is ln of 5 over 2 over 4. Yes, I know, this is approximately 0.229. Yeah, I'll just leave it like that. Now, what is the time t? Well, it says how many bacteria will be there in 24 hours from the start. So our t is going to be 24. Okay, so what I just did here was I just copied the previous page. So we're looking for A sub 0 is 200, K is approximately 0.229, and T is 24. All right, so let's go back to our formula again. A equals A sub 0 and then e to the k t. All right, again, A is what we're looking for, so let's just plug in chug. So this implies that our A is A sub 0, which is 200, and then times e to the k, which is approximately 0.229, and then multiplying here by 24. Okay, now we need to type this in our calculator. Now, depending on what kind of calculator that you have, your order of inputting might be a little bit different. But if you have a graphing calculator or scientific, you should be able to just type in 200 and then times and then find the E button. So mine is second ln, so let me go with second natural log, and that should give me E to the. Now you're going to have to type in 0.229 times 24. Now, if you look at your calculator, right, this might be what you're seeing right now. So you got 200 asterisk e to the, and then here comes the parentheses to insert your exponent. All right, so here you can just type in 0.229 times 24, or if you want to be safe, you can put another parentheses, 0.229, and then times it by 24, if you want to. All right, remember, your graphing calculator or scientific calculator, order of operation matters. All right, so let me type that in. So we got e to the 0.229 times by 24, and parentheses closed, and then I hit enter. Then what I got was, let me see, our A is approximately 48743.02. all right, so it looks like our A, which is the number of bacteria after 24 hours, is going to be 48,743. All right, so let me just box this. So what we have just solved for is that at our rate k, which was approximately 0.229, the number of the bacteria at the end, meaning after 24 hours, you can expect to have 48,743 bacteria. So I'm just gonna write that out. At this rate of growth, there will be approximately 48,743 bacteria after 24 hours. All right, so this is gonna be our final answer. I'm going to stop here, so if you have any questions at all, please let me know. And if you need any help with inputting in your calculator, I'm here to help you. So you just need to let me know which calculator that you have so that I can assist you better. But anyways, great job, and I'll see you soon.